Hi, I'm Luke Kane. Welcome to Algebra 1. Today we're going to talk about slope and how it applies to parallel lines. You may recall at our last lecture we talked about the slope of a line and we defined it as the rise over the run, the change in y divided by the change in x. Today we're going to use that information to determine if two lines are parallel or not. Here is the equation of a line written in slope-intercept form. This y to the x is a function notation which we haven't got to yet. Think of it for the time being as just simply y. And y equals mx plus b. M is the slope of the equation and of the line, and b is the y-intercept. So let's take a look at what that equation might look like if m was 1.19 and b equals 3.37. Would look like that. Here's b here, and the slope is depicted as the rise over the run. In this case, let's make the slope a little easier by making it an integer. Let's make it 1. Okay. So, and let's move the intercept down. So we can put this any place we want it. And by making that an integer, we can now actually count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 centimeters in the run. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the rise, and hence the slope is 1. And of course, the bigger m gets, the more the rise. You notice the run is staying the same. And of course, when m is negative, the rise is actually a fall. So, in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 over 10. 10 over 10 is 1. And it's going down, so it's negative. This is all old hat. Now let's talk about more than one line. All right, let's start here. Okay, so here we have two lines. Each of them represents one equation. Here's the first equation. y1 equals m1x plus b1. That's the red line. Here's its y-intercept b1, which is at 4.43. Here is y2. The second line, the blue line, intercept is down here, just a little bit below 4, and it's a steeper. It's got a larger slope, so it's a steeper incline. Now let's see what happens when I set the slope to the same number. I set that one to 2, and I set that one to 2. Looks like they're parallel. All right. Let's prove to you that lines that have the same slope must be parallel. All right, let's prove that if two lines are parallel, if two lines have the same slope, they must be parallel. And we'll use this case here. Now, let's do some definitions. Let's call this red line, line 1, and let's call this blue line, line 2. And let's define slope 1, let m1 equal the slope of line of L1. Similarly, let m2 equal the slope of line 2. All right, we're going to define some angles come into this. Let's call this angle theta. It's the angle between line 1 and the x-axis. Okay? That's theta, and we're going to define another, and let's call it theta 1. And let's call this angle over here theta 2. And it's the angle between L1 and the x-axis. Alright, so we let theta 1 be the angle between L1 and x-axis. And we let theta 2 be the angle between L2 and the x-axis. All right. So what are we going to do? We're going to start with this as our first step in proving this. M1 equals M2. The two slopes are equal, and this is given. All right. Now let's look at this a little more carefully. We're going to look at the slope now graphically. So the slope of M1. Well, to represent that graphically, I have to draw this right triangle. And it has a rise. Let's call it rise 1. And it has a run. Let's call that run 1. And we can do the same thing for line 2. Oops, that's not exactly very straight. Let's try. See how straight. Well, it's not too straight, but it serves a purpose. This is a right triangle. It's bigger, so it probably has a bigger rise. So let's call that rise 2 over run 2. All right. So we can now substitute that into this. So we now have rise 1 over run 1 equals rise 2 over run 2. And why is that true? That's true by the definition. Oops. Definition of slope. All right, now we got to do another definition. And this definition is going to be the definition of tangent. All right. Some of you may remember from trigonometry or geometry the mnemonic saw, ka, toa, which defined 3 trigonometric functions. This defined the sine function, and what they all have in common is they all have an angle. Let's call that angle phi, phi, pho, phum. And the side of the triangle, and it's a right triangle, and the side that's opposite is called opposite, and the side that's adjacent to phi is called adjacent. Obvious sorts of names. And the longest line in a right triangle is called the hypotenuse. So as you may recall, the sine of phi was the opposite over the hypotenuse. Opposite over the hypotenuse. The cosine of phi was the adjacent over the hypotenuse. But what we're interested in is the tangent. And the tangent of phi is equal to opposite over adjacent. Now, if we look at our two triangles up here, guess what? The rise is the same thing as the opposite angle of phi 1, and the run is the same as the adjacent. So with that little bit of information, we can now say, because this is true, we can say that the tangent of theta 1 is equal to the tangent of theta 2. Because for theta 2, it's also true. This is the opposite, of theta 2, and this is the adjacent of theta 2. So consequently, this defines tangent of theta 2. Alright, theta 1 equals theta 2. Well, that can only be true if theta 1 equals theta 2. Or, in more geometrical terms, theta 1 is congruent to theta 2. Okay, now, this is significant because this is going to get us to where we want to go. The x-axis can be looked at as a transversal of two lines, and theta 1 and theta 2 are corresponding angles. So let's put that down here. Theta 1 and theta 2 are corresponding angles. Therefore, since they're corresponding angles, therefore, line 1 must be parallel to line 2. Why? Well, this is an old theorem from geometry. So we can stop here with the notation QED, quod erat demonstrandum, which is Latin for meaning that's what we wanted to show. So what we wanted to show is that if the two slopes are equal, then the lines are parallel. So what did we learn today? Basically, we learned that if two lines are parallel, then their slopes are the same. This will come in handy when we need to determine whether or not two lines are parallel or not. We need to find out what their slopes are and simply compare them. Okay, next time we're going to talk about finding out if the equations of two lines are perpendicular or not. Till then, I'm Luke Kane. Thanks for watching. Bye now.